Suppose that I have a very long piece of rope, and suppose that I have a friend standing on the left and another friend, green color one, standing on the right, and each of my friend starts shaking at one end of the rope. So create a wave in the rope that starts traveling away from them, like that. So this wave travel to the right, and that other wave travel to the left. I'm going to try and understand what happens when these two waves meet. Now I'm going to assume that they are swinging the ropes up and down at the same frequency and with the same strength. So this means that I'll have two identical waves traveling towards each other. It's exactly the same. What happens when they meet? That's the question I want to answer. Now we have learned, I've explained, talked about superposition. So this is what I'm going to do. I'm going to try to use the idea of superposition to understand this. Let me, the idea of the superposition is that I'm going to think about these two waves separately, as if they can cross through each other, like the other one does not exist, and then I would, when they are at the same place, I would add up their displacements at every point. So let me start. I'm just going to draw this dotted line. I'm going to draw this dotted line, and I'll use different colors to represent those two waves. Now let me use blue color for this wave coming from the right. Blue color for this one. So suppose that when the wave reaches somewhere in the middle, it looks like this. Alright, and this is the wave that is going to the right. This is what you see if the other wave is not there. But there is that other wave, of course, that other wave from my green friend going to the left, and that other wave would overlap with this wave. So and they are always moving. So let's say at some point in time, the other wave is here. Let's say I pick a time when they overlap almost exactly. They overlap almost exactly. And this green wave going to the left. What happens when they overlap almost exactly? Well, we would, from the principle of superposition, we would expect them to add, the displacements to add. So let's say at this peak, both have upward displacement. So when they add together, I will get a higher peak. I'll get higher peak, maybe up there somewhere. And here, where both have downward displacement, I would expect that when they add, it would be even lower. So that point would be, peaks will become higher, the troughs will become lower. And at the point where they cross through the rest position of the string, there will be zero displacement. So that's still 0 there, 0 there, 0 there, there, and there. So therefore the resultant, the combined effect, right, when they add together, is this. So I'll get a wave, what looks like a wave with a bigger amplitude. Okay. one question, this resulting wave, is it traveling to the right or to the left? Right, I have one wave to the right, one wave to the left. So when they meet and give this combined result, a wave with a bigger amplitude, which way is it going? Well, if it makes any sense, it's not going anywhere. All right, somehow the two directions cancel. So let's find out what actually happens. Now, to make things easier to see, I'm going to draw some vertical lines just to mark the positions. So that's one line going through this point there where it crosses the rest position. Okay. Now, and I'm going to need some way to follow each wave so that I know where they are. And I'm going to do this. I'm going to imagine that I can just focus on, say, one of the peak in each wave. Let's say this point here. Let's say this crest I will follow with my eye as the wave moves to the right. And let's say when it moves to the middle, it is this one. Okay, the blue crest has come here. And then the green one, okay. Wait, let's say the blue crest is here. Okay, that one. And let's say the green one, the green wave, I'm going to focus on, say, this peak, this one. So as it moves, I follow that peak with my eye there. And let's say it at this point where they meet, let's say that green peak has come here. So I'm going to follow each of these peaks and see what happens after a short time. So let's say after a short time, say maybe a bit later. Okay, a bit later, I'm going to draw. Okay, I'm going to draw another wave. So what happens to that blue wave? So I'm following this peak, right? And this blue wave is moving to the right. So let's say that after a short time, this peak moves to here. Right? It moves to here. Now I'm talking about one wavelength. That's one wavelength, right? Let me remind myself. So from there to there. Okay, must not forget this is a different scale from there. I've magnified this, hopefully to make things clearer. So from there to there is one wavelength. Okay, that's one wavelength. Right, so let's say now the blue wave, the peak of the blue wave has moved to there. So that's by a quarter of a wavelength. So the blue wave is moved there. So that's the peak that I was following. It has moved to here. Okay. Try to draw the rest of the wave. Looks like this. So that's my blue wave, still traveling to the right. Let's have a look at the green wave. The green wave, that peak would have moved to the left also by a quarter of a wavelength, since they both move at the same velocity. So that peak would have moved to here. Okay, so now if I draw this wave traveling to the left, try to draw that, I'll have a peak here, trough there, peak there, and a trough here, and a peak here. So that's what it looks like after a short time. Let me now take a step back and look at these two waves. See, where I have a peak of the blue curve, now I have a trough. So the displacement here is up. The displacement from the green wave is down. They are in opposite directions. So when I add them, they have to cancel. And it's the same here. Okay, so when I add those two displacements, the resultant will be here at the center. And it's the same here. The peak of the green wave is at the same position as the trough of the bottom of the blue wave. So when I add the displacement, they will cancel. And here, for example, both wave goes at the rest position. So it's just zero displacement. And if you follow through the whole wave, you find that all the displacement add to zero because we have because the displacements are always opposite. So therefore, I would get just a horizontal line. The resultant is as if there is no wave. Okay, and a bit later again, let's see what happens. Let's try to follow that peak of each wave again. So I have this blue curve still going to the right. I'm following this peak, and after another quarter of a wavelength, it would have moved there. That's the blue peak would be there. So I'll try to draw the whole wave in this around here. So that's the blue curve, and the green curve, if I follow that peak would have moved by half a wavelength to the left, and that would be just happen to be here. So that peak is now there. If I draw the green wave now, or it will meet with this blue peak. That's the green wave. Okay. Now I'm back to the first, what looks like the first position, where the two waves meet exactly. So the peak meets the peak, and the displacement will add to give you a bigger displacement. So these two displacement will add to give you a bigger amplitude. Those two displacement downward would give a bigger downward trough. Likewise for this and for this. So those were the points that cross the rest position, these points will still be zero. So I can now draw the resultant, and it would look very similar to the first one. Try to draw it. That's the resultant. Looks like a wave with twice the amplitude. Okay. Looks like the first one, but if you look more carefully, you see that it is flipped upside down. It is as if the top one has been flipped. Okay, the peak now becomes the trough. Okay. So let's try to follow through the motion. Let me follow a point, say this point. This particular point, for example, on this wave. This point here, after a short time, a bit later, would have come down to here, right? And a bit more later, that point would have come down to here. Now what happens even later, all right? A bit later again, we would expect this point to go back up, and it will just go up and down. As if you remember, that's also what happened when we shake the rope up and down and you get the wave. Each point although the wave looks like it's traveling to the right, each point on the rope will just be going up and down. Right? It just gives the appearance of a wave going to the right. So that's what will happen in this pattern. Each point will be going up and down. Okay, so after a short time, this point will go back up, and you will get this. It will get to look like this again, and then it will go back up to the top. Now, if I look at that point, now look at this point here. After a short time, this point will still be at the same position, right? Because here the peak meets the trough, and the resulting displacement is still zero. A bit later, it's still here. So we have a point that never moved. All right, and that's unusual because remember, if I have the separate wave on its own, the whole wave moves. All right, and every point along the wave would be always moving up and down. All right, there's no point on the wave that is at rest. But in this combined result of two waves in opposite direction, I actually get points that stay at rest. Okay, let's follow on and look at one or two other more points. So this point here at the trough, label it with a triangle. After a short time, it would have moved up to here, the rest position. After a short time, it would have moved up. So this point would be moving up and down. So we'll carry on. This point here would just stay at the rest position. And then the pattern repeats itself. So what you see here is that when the two waves in opposite direction meet, I have a situation in which, okay, the amplitude becomes doubled at certain positions, but there are also certain positions where the string appears not to move anymore. All right, certain points on the string that appears not to move. Okay. Now this picture, as it is often joined, is often drawn together with this to show this wave pattern. So this is how it's normally drawn. That the three resultant waves are often combined into something that looks like this. Wave that goes up and down like that. And that wave is often drawn together with this wave. This wave at the bottom that looks like this. So that's how it's often drawn. And what this represents, it doesn't mean that you have two waves like that and like that at the same time. It just means that at one instant, the wave is like this, and a bit later, the wave is like this, and a bit later, the wave is like this. So you have this point here, which always move up and down, here, but you have also points in between them that is always at rest. So those points which are always at rest are called nodes, and those points which have the biggest amplitude is called the antinode. And in between the antinode and nodes, there are other points like this one, which also go up and down, but not as much as at the antinode. Okay. Now this kind of wave, if you look at the peak, for example, the peak just goes up and down. Unlike this wave, if I just have one wave with my friend shaking it, the peak would actually be traveling to the right. Here, the peak won't actually travel to another place. It will just move up and down. So you can see a very obvious difference between these two kind of waves. And because this kind of wave, each peak of this kind of wave, it doesn't go to another place. It just goes up and down on the spots. It has a name. It is called stationary wave. Now the name. Stationary wave. That's one name. It is also called another name. It is also called a standing wave. Right? And one thing that we should note about this wave is that if you remember, on this kind of a wave that actually looks like it's traveling, okay, let me write down the name of that kind of wave as well. This kind of wave which looks like which actually travels to another place, it has also a name. It's either called a progressive wave, or we can call it a traveling wave. A traveling wave. So we have two types of wave. Alright, there are these two basic types of wave, the traveling wave and the standing wave. And it means something about the energy. A traveling wave actually carries energy from one place to another. Right? You can imagine that as you shake this wave goes to another place, and that very motion of that wave, the up-down motion at each point of the string, has energy. But in this case, the peak, the rope is just going up and down. The peak is just staying on the spot in a standing wave. So in a standing wave, the energy stays there. That energy is not carried to another place. So that's something about the energy. And if I now look at the wavelength, okay, we know that wavelength, this is one wavelength, one cycle, and on the standing wave is the same. This is one wavelength, but it's very easy to, from this picture, to think that one wavelength is just from there to there. It's very easy to think that that is one wavelength because that looks like one repeating unit. But in fact, that is half a wavelength. This is half a wavelength because one wavelength has to go from there all the way to there. So the important thing is to remember that this pattern that is we often seen when we see pictures of standing wave, alright, it's really two waves drawn together. This is one wave. Okay, that's the other wave. So which is why one wavelength goes from here to here. Okay, so that would be one wavelength. So finally, because of this understanding, as you can see, we got this wave pattern. We can get this standing wave pattern when we have two waves that have the same amplitude and the same frequency meeting each other. That is also how we can define the meaning and also explain the reason or one reason for having a standing wave. A standing wave or stationary wave happens when we have two waves of two identical waves. Two identical waves, meaning same frequency and same amplitude, in opposite directions, meeting each other.